Okay, section 7.5, applications of rational expressions, rational equations and rational expressions, to be honest. We're going to start off with some formulas. So solving formulas for specific variables. We've been doing this a couple times this year. Now we're going to do ones that involve rational equations or rational expressions. So recall that a formula is just a mathematical statement that has meaning, right? So in class, we've had things like 2x plus 6, or 2x equals 6, which we know x equals 3, but it really has no real-life connotation. The formulas, however, have meaning. If you see something like area equals length times width, then notice even I just said, I didn't say A equals AW times L because nobody ever says it that way. It's area equals length times width, right? We automatically know what that formula means. Also recall that just because a formula has meaning, which is great, that's their purpose, right? It's definitely good to know what they mean. It doesn't mean you can't solve it if you don't know what it means, okay? So if all of the formulas we will be doing, even if you don't know them, you can still solve them. They follow all the same algebraic properties, okay? We are actually not going to do this first one because I'm realizing there's a typo in there that makes it physically impossible. So we're not going to do that one. Chances are it's actually not even in your notes, so you don't need to worry about that. But I just want to let you know I will be starting with B, which will be down here. And we're going to solve for a specified variable. Okay, so formulas, remember, they have multiple variables, right? They've got i's and e's and r's and n's and stuff like that. And it's very important to note that this r and this r are not the same r, right? If it's a capital R and a lowercase r, that's like radius 1, radius 2, right? So you don't want to say those are the same. When you're solving for a specified variable, you treat everything else like it was a number, like it was a constant, okay? So you really just have to find which one you're looking for. I'm looking for n here, n right. N, and I treat everything else exactly the same, and I have two n's actually. So let's start doing that. Let's pretend I want to get n all by itself. And let's not pretend, I actually do. So I'm going to get n all by itself. First off, I'm actually going to get rid of the rational part of this. I'm going to change this, and I'm going to change it into not irrational. So I have n e over r plus nr. Now from our last section, remember when we multiplied the denominator to both sides so that we got rid of it? Same concept here. It's not going to go away, but it is going to be on the other side. R plus nr. So I end up getting r plus nr times I is equal to it's equal to ne. Fabulous. Do I want to do it? Yeah. Okay. I can distribute the I in, so I get IR plus INR is equal to NE. I can move that one over. IR is equal to NE plus INR. Now I notice I have an N in both of these guys, so I'm going to zoom up here. Okay, so I'm going to take out the n. So over here I'm left with IR is equal to n times e plus IR. And then I'll divide by this side. So divide by e plus IR. Divide by e plus IR. And I end up with n is equal to I capital R over e plus I lowercase r. So I just had to switch the variable around a few times. Really the only thing that involved the rational was that first step, that multiplying by the denominator on both sides. After that, I distributed, right? Distribute, move any n terms to the other side, take out the n, and divide, oops, plus I. And you end up getting n all by itself. Cool. That should pretty much be a review. Let's go try C now. So we're going to jump back up to C. This one's a little more rationally. I've got capital P, capital V over capital T is equal to lowercase p, lowercase v over lowercase t. And I want to solve for capital T, right? Capital T. So I'm going to treat everything else, including lowercase t, like it's unimportant. I want to get everything away from capital T. Okay. First thing I want to do is get rid of these denominators. It may not get rid of the denominator in both of them, but I have PV over T is equal to PV over T. I'm going to try and make my P and V really small and curvy so that you can see they're the same. They're different. I need T to be in the numerator, right? I need it to be in the numerator because what I have right now is divided by T, and that's technically 1 over T. I don't want that. So I'm going to multiply by T to both sides. Capital T. Capital T to both sides. So those two T's are going to cancel. Now my T is over on the right-hand side. That's okay, right? It doesn't matter. N was on the right-hand side to begin with in the last problem. So I'm left with capital P, capital V is equal to lowercase p, lowercase v, capital T over tiny t, right? Okay, next I'm gonna get rid of the other denominator, multiply by t, and I end up with lower, upper, upper, lower, lower, upper, because those two t's are gonna cancel. Then finally I'll divide by the two lowercase ones, whoops. And finally, I end up with lowercase t, capital P, capital V, over lowercase p, lowercase v is equal to capital T. And since capital T is all by itself, I am done. Remember, with formulas, it doesn't matter what the other side looks like. The goal is to get one of them by itself. Okay? The goal is to get one of them by itself. In this case, we just had to deal with the fact that the t was in the denominator first. So we had to get rid of the denominator. And we're done. Cool. Let's try one more. Y is equal to x plus z over a minus x. We want to solve it for x. So again, don't panic if you see a rational. You just want to get rid of the rational part first. So get rid of it. I'm going to multiply ax to both sides. So I get a minus x times y is equal to x plus z. So in other words, I move this denominator and I put it over there. Put it over there. I will now distribute the y. Ay minus xy is equal to x plus z. I want to move all of the non-z terms to the non-x terms to one side and all of the x terms to a different side. So I think I will add this xy, subtract the z, and subtract the z. So these z's are going to go away. I'm left with nothing but x and xy. Here, the xy's are going to go away, and I'm left with ay minus z. I see no x's over on the left-hand side. Now I will reverse distribute. I see a common factor of x here. Ay minus z is equal to x. When I take out the x from this first part here, I'm just left with 1. Take out the x from the second part, I'm left with y. And then I can divide by that, and I get that. Let's see. Ay minus z over 1 plus y is equal to x. So again, very little actually dealing with a rational, right? It's very little of dealing with a fraction. It's just get rid of the fraction first, and then start moving stuff from side to side until x is all by itself. There we go. Alright, that is solving for a specified variable when it has a rational in the equation. Let's go on to some different types of applications. So applications you might see, some real life context here, right? Because why are we even doing this? Who cares, right? This actually happens quite a lot. There's quite a few different rational equations that will pop up in your lifetime, regardless of where you end up. It happens in business. You'll see it happens in distance, and it happens in work rates. There's a whole mess of other ones that I would be happy to discuss with you. Come in and talk to me. But the three we're going to be talking about are proportion, distance, and work rate. So, solving proportion. A proportion. What is a proportion? A proportion is a statement that looks like this. You are comparing two fractions. So, 5 out of 10 people is the same thing as 1/2, right? Or, like 1/2 of the people, right? So, it's a proportion that compares two fractions. So, it's a rational equation that we've kind of seen. Kind of when we're solving them, we get down to this point, we want to get down to a proportion. Let's see what that looks like in example 2.1. In 2003, about 15 of every 100 Americans had no health insurance. The population at that time was 288 million. How many Americans did not have health insurance? So basically, we're breaking this down into two different statements. 15 of every 100 Americans. That's a proportion, right? So that's a fraction, right? 15 of every 100. That is a fraction that looks like 15 of 100. Or 15%, right? 15%. That sucks, but yeah. It also tells us that the population was 288 million. So that was the total population, right? Total population was 288 million. That would be the 100% of Americans. And then they ask how many of those 288 million did not have health insurance. So that is the question. And we have translated. So what you want to do is set up a proportion kind of like this. They tell you one thing, a 15 out of 100, a 47 out of 32, or whatever it is. And then they tell you another part, and they want you to compare the two. Now when it comes to actually solving these, we can use our just basic solving rationals. So I'm going to, let's see, I want to get rid of the denominator. Multiply by 288 to both sides. I'm left with x. Let's see, 288 times 15 divided by 100. 288 times 15 divided by 100. It's going to be times 15 divided by 100, 43.2. 43.2. Now what does that mean? That's our solve step, right? We solved it, x equals 43.2, but that means 43.2, careful the units, million people did not have health insurance in 2003. That's a lot of people. That's a lot of people. 43.2 million people did not have health insurance. Now, I don't care what your stance on Obamacare is, that sucks. That's a lot of people without health insurance, so that sucks. Alright, cool. So that's one of our proportion problems. Easy peasy. Let's go on to the next one. Marissa's car uses 10 gallons of gas to travel 210 miles. She has 5 gallons of gas in her car and wants to know how much more gas she will need to drive 640 miles. If we assume the car continues to use gas at a constant rate, at the same rate, how many more gallons will she need? Well, let's see. So we know that we've got one proportion here, 10 gallons of gas for 210 miles. So we can do gallons per mile. So you always want to set it up units by units. Notice in the last one it was people who had health insurance, or no health insurance, total, right? So you always kind of want to take it out of the same units. So 10 gallons for 210 miles, pardon me. And we're curious about 640 miles, right? How many gallons is that going to take? But let's be careful, right? So she wants to go 640, but she already has something in her car. So we're not asking about the total number, we're asking how many more. So she already has 5, and she needs more. There, now we have a proportion, 5 plus x, right? So we translate it. Let's solve now. Let's multiply 640 to this side, 640 to that side. Let's see, 640 times 10 is 6,400 divided by 210. It's not great, so I'm going to leave it as a fraction. 4,000 divided by 210. Cut off at least a 0 from both of those. So we'll do 640 over 21 is equal to 5 plus x. Right, 5 plus x. Okie dokie. And then I can subtract 5. So x is equal to, we'll just make it a decimal, it's fine. 30.5 minus 5. So about 25.5. I don't know why I didn't just do that in my head. Alright, we solved. X equals 25.5. So what does that mean? It means she needs 25.5 more gallons. Alright, proportions. Pretty easy, right? Proportions are nice. Proportions, once you set them up. It's kind of tricky setting them up, but after that, they're pretty nice. Okay, distance, rate, and time. This is an equation you will want to memorize as fast as humanly possible. Distance is equal to rate times time. Distance is equal to rate times time. When we were solving for formulas, I told you it's okay if you don't know them, and that still is true. But this one you need to memorize because we're going to use it so many times. So we have distance is equal to rate times time. So let's see one of the problems. A paddle-wheeler goes 10 miles against the current in a river, and in the same time it goes 15 miles with the current. So it goes against the current and then with the current. If the speed of the current is 3 miles per hour, find the speed of the boat in still water. In still water, okay. So there's actually two different distance equations going on here. So I'm going to make a little table. This one's going to be about upstream, and the bottom's going to be about downstream. Okay? And I'm going to look at the distance, the rate, and the time of all three. Okay, kind of hard when you have a box to write in, but that's okay. Distance, rate, and time for all three. Alright, the distance in this river, let's see, did it tell us how long the distance goes? No, it doesn't, okay? So they told us there's 10 miles going up, oh, it did, sorry. It goes 10 miles going up, and it goes 15 miles going back, right? 10 miles going up, 15 miles going back. Sorry, one sec, got my calculator. Okay, cool. Now, let's take a look at those rates. So when he's going upstream, against the current, that's upstream, right? Fighting the current. You have to fight that current. I don't know the current yet. That's actually the question. Find the speed, right? So I'm going to call the speed x. This is the speed, this is the current, right? If he's going and fighting this one, and I'm sorry, this is not the current. This is the speed of the boat. So the current is 3 miles per hour. He's fighting this 3 miles per hour. So whatever his speed is, he's taking off 3 miles per hour every time. If his speed was 15, he's only going 12, right? If his speed is 45, he's only going 42 because the current's pushing him back 3, right? Same thing, it's kind of the same but opposite for going downstream. Whatever his speed is, he's actually going 3 miles faster because the current is pushing him, right? If he's paddling at 15 miles per hour and the current is 3 miles per hour, then it's actually going 18 miles per hour, right? So it's pushing it down. So that's how you can figure out those. The time, I don't know. I know it takes him, actually don't know anything about the time. Same time, okay. So he went up and down the same time, but I don't know anything about that same time, right? So what I can do is rewrite this using my formula. I know that distance is equal to rate times time, right? Let's solve that for time. So we'll solve that for time real fast, get time by itself. We get t is equal to d over r, right? T is equal to d over r. So in other words, time going upstream is d over r. In other words, upstream would be 10 over x minus 3. Same thing over here, 15 over x plus 3. That's his time going down. His 15 miles divided by the time per hour, right? The time per hour. And we have our 2 times. Okay. I know these times are the same, which means this expression is the same as this expression. Is the same as this expression, right? So I can set those two equal to each other. I know it took him the same amount of time. Now I can solve using rationals. Since I noticed I kind of wrote that big, I'm going to write it a little smaller. I'm going to write it a little bigger. So I have 10 over x minus 3 is equal to 15 over x plus 3. Now I need both sides to be the same. So what's missing from the left side would be an x plus 3 over x plus 3, right? What's missing from the right side would be an x minus 3 over x minus 3. And here here I end up getting 10x plus 30 when you multiply the tops, and then over x minus 3, x plus 3, right, is equal to 15 x minus 45 over x plus 3 and x minus 3. So I've just multiplied the tops and made the bottoms the same. When the denominators are the same, they cancel out, right? You can multiply by both to both sides. They go away. Just left with 10x plus 30 is equal to 15x minus 45. So I can add, let's see, subtract 10 to this side, subtract 10x to that side. You get 30 is equal to 5x minus 45. Add 45 to 30. Is 75 divided by 5 is 15. So x equals 15. And I have solved. Translate back, that means x was the speed of the boat in still water. It's 15 miles per hour in still water. And again, that was actually coincidence when I said 15 plus x, all that jazz. I had no idea. I was just solving. Okay. That's pretty much it. So start with one of these charts. Remember way back when in chapter 6 when we first started using distance, rate, and time, we still used one of these charts. These charts will definitely help you when setting up expressions like this, okay? When setting up things equal to each other, that's going to be super important, knowing what the formula is and how it plugs in, okay? All right, let's do another one. Okay. At O'Hare International Airport in Chicago, Cheryl and Bill are walking to the gate at the same speed to catch their flight to Akron, Ohio. Since Bill wants a window seat, he steps onto the moving sidewalk and continues to walk with Cheryl while Cheryl uses the stationary sidewalk. If the sidewalk moves at 1 meter per second, Bill saves 50 seconds covering the 300-meter distance. What is their walking speed? All right. So again, we're using distance equals rate times time, right? Let's again set up one of those tables. That's not where I wanted to set up that table. So let's set up one for Cheryl and one for Bill. Let's think about distance, rate, and time. Distance, rate, and time. Alright, so it says that they walk the same 300-meter distance, so they will both be walking 300, right? 300. Okay, cool. That was the easy part. Oh, sorry. I guess my sound cut out there. Okay, so let's call Cheryl's speed x, right? Because they want... So if Cheryl's moving on the stationary sidewalk. Cheryl's moving on the stationary sidewalk. So her speed, that was weird, is equal to x. We don't know it. We don't know it. That's kind of the question. But we do know that Bill is going the same speed and the 1 meter per second more. So Bill is going to be x plus 1. So those are their corresponding rates. Cheryl will be the x. Bill is also walking x, but he's also going a meter faster. Very similar to the river problem, right? Alright, once again, we don't know anything about the time. We do know that Bill saved 50 seconds, right? Bill saved 50 seconds. But we don't know anything about the time of Cheryl versus the time of Bill. We don't know anything specific. So let's just create that same kind of equation. We know if distance equals rate times time, then that means that distance over rate is equal to time. So for Cheryl, that would be 300 over x, and for Bill, that would be 300 over x plus 1. Okay. Now we do know that Cheryl, we do know Bill, sorry. We know that Bill saved 50 seconds, so his time would be Cheryl's minus the 50 seconds, right? So Bill is going to be Cheryl's time, take away 50 seconds. That's what it's going to be. I know Bill was 300 over x plus 1. And I know Cheryl was 300 over x minus the 50 seconds. And we have our equation. Alrighty, let's go ahead and solve this. So that was the translate part. Let's solve it now. I'm going to go over here. So what's missed? So the LCM here would be x plus 1. And, yep, x plus 1, because that 50 is over 1. So x and x plus 1, right? Times that to both sides. So what's missing from the right-hand side, or the left-hand side, pardon me? The x part. So x times 300 over x plus 1. That's not right. Oh, x over x. Sorry. Oh. Hold the phone. Oh, no, that's right. That's fine. Yeah, that's okay. Okay, and then we have the 300 over x. We're missing the x plus 1, And the 50 is missing both of them. And I've totally run out of room, so I'm going to erase this guy. So the 50 is missing both of them. So 50 times x plus 1 over x plus 1. Alright, we end up with 300x over x plus 1 is equal to 300 times x plus 1 over x plus 1 and minus 50x plus 1 over again x plus 1. Now the denominators are the same, so I end up with 300x equal to 300x plus 300 plus, let's see, 50. If I combine all that, that's 50x squared plus 50x. Okie dokie. Lots of stuff to combine, lots of stuff. I have 300x on both sides, so those cancel. I end up with this equals 0. Now I have 50x squared plus 50x plus 300. Alright, now I can factor that. Well, I see a GCF here. I can take out 50. 50 and 50. I want to say 6. Yep. So I'm going to sneak up here now. Sneak up here. Sorry, I'm not CellCon. I don't have infinite number space here, but that's okay. So I'm just going to sneak up here. So I have 0 is equal to x squared plus x plus 6. Alright, what multiplies to 6 and adds to 1? Oh, I'm sorry. This should have been a minus here and a minus there. So that would divide by a minus 50. That makes this a minus 6. My apologies. Minus 6. That makes more sense. Multiplies to negative 6 and adds to 1. Negative 3 and negative 2. So x plus 3, x minus 2. That means either x is equal to negative 3 or x is equal to 2. Okay, that's my, so I solved. Right now I have to translate back. Which one of those actually makes sense as a walking speed? The 2. So this answer would be 2 meters per second. That's how fast they were walking, which is pretty dang fast. 2 meters per second. They must both be running for this flight. Okay, so setting up a table, setting up an equation, solving. We ended up having to factor in this one. That's okay. We ended up having to factor, and we ended up with two different answers. Which one of those actually made sense as a walking speed? 2 meters per second. Alrighty. Let's go. Alright, so the last type of problem we have is called a work rate problem. You probably have heard of these. It takes, let's read one. Letitia and Kareem are working on a neighborhood cleanup. Kareem can clean up all the trash in his area for 7 hours, while Letitia can do the same project in 5 hours. How long will it take for them to do it together? So you've heard these, painting the fence, 2 together, right? How long will this person takes this long, that person takes that long. How long does it take to do it together? Very classic problem, still very applicable. Work units are very important to know. So work is also equal to rate times time. Okay. Work is also equal to rate times time, right? If you work for 3 hours at a rate of 2 hours per, or 2 miles per hour, you can get a total of 6 miles, whatever that is. But basically, here's the unit. It's 1 over T. Okay, so 1 over T, that's your work. Your work. Okay, so kind of ignore what I said about that. That's not really true. This is equal to work for one job. So you've got a job that needs to be done. If you can do it in 6 hours, your rate is 1/6. Okay, 1/6 of the job can be done. Back to Letitia and Kareem. The same idea. We can set up another table. Set up another table because those are very useful. One for Kareem and one for Letitia. So Kareem, if he works for, let's say his time is, his time was 7 hours, right? And no, let's not do it that way. Let's just call it his work. So his work rate was, if he was working for 7 hours, his work rate is 1 over 7. For Letitia, if she's working it in 5 hours, her work rate would be 1/5. Okay, that's basically just the units that go with it. Their time working together, we know nothing about. So work together, we'll do time together. We don't know about it, but we do know it's the same amount, right? We know that however much they work together, it's impossible for one person to work more together than another person, right? That doesn't make any sense. So they both have the same amount of time together. Therefore, the fraction that gets done by Kareem, so the fractional part of the job, the part that Kareem does is going to be his work rate times that time they work together. And the part that Letitia does is going to be her work rate times the time together. So that's how we get this fractional part of the job done, right? So Kareem's going to do 1/7 of the job, Letitia's going to do 1/5 of the job, right? And then times the time they work together, that's going to be the whole job. And finally, we can set up an equation. Kareem's work and Letitia's work is going to give us that one whole job. That one whole job gets done. That whole cleanup. We have translated. Good. So the translation really just comes down to your work rate, 1 over T. Let's go ahead and solve that now. Well, I'm going to need to put these into a least common denominator, right? Technically, I can see this as x over 7 plus x over 5 is equal to 1 over 1, right? That's another way I could think about it. And this is actually a heck of a lot easier than the other rational problems because none of the x's are in the denominator, right? So what's the least common denominator between 7 and 5? That would be 35, right? Well, 7, 5, and 1, right? But that would be 35. So I'm going to make everything 35. In the first equation, I need to multiply by 5 over 5 to the x over 7 plus a 7 over 7 to the x over 5 is equal to a 7 and a 5 over the 1 over 1. So I end up with 5x plus 7x equals 35. Yep, 35. Sorry, not 7 over 7. Yeah, no. I just, not this one. You only multiply by what's missing. Alright, so now I can go over here because I'm running out of round. I'll just keep going down here. Combine like terms. You get 12x equals 35, or x equals about 35 divided by 12. Well, let's see. That would be about 2.9-ish, but that was a horrible 2.9. My apologies. 2.9-ish. Or let's say, okay, you've got 35 over 12. So 35 over 12. Let's set up another proportion to that over 60 minutes. How many minutes would that be over 60 minutes? Let's see. So that would be, let's put an X there. Multiply by 60. Multiply by 60. You end up getting 35 times 60 divided by 12. 175 minutes is equal to, let's see, that's divide that by 60. 2.9. Let's see. Take away 120. That would give you, so let's see, that would be 2 hours. Take away the 120 minutes. Take away, sorry. 55. So 2 hours and 55 minutes. That's how long. And that was more of our translate back part, this converting back here. X equals 2.9. You could say 2.9 hours if you wanted to. Or you could just convert it back using a proportion to make a much more realistic answer of 2 hours and 55 minutes. That's how long it will take Letitia and Kareem to do both. Alright, so we talked about three different kinds of problems and solving formulas. I hope that helped. Otherwise, feel free to email me, and I will see you next chapter.